Hello, my name is Hunter Howell,
Hi, my name is Reece Bawden.
Hello, my name is Jason Blanchard.
and today we are going to be talking about the effect of intermittent cold exposure on energy consumption. Many of us have an ideal that we want for our bodies. We have our goals and we have things we're working towards. For many of us, that involves probably losing a little bit of a weight that we so unwelcomingly have. And we found that this may be a very viable solution to be able to do that. So, energy consumption is all about metabolism. It's about how much energy we're using versus how much energy we're intaking. And if we can shift our energy intake so it's less than our energy output, that's where the weight loss happens. And we found that a way to do this could potentially be through the activation of BAT through intermittent cold exposure. To understand how this works, you have to understand how beige adipose tissue works. So, beige adipose tissue, or BAT, is a type of adipose tissue that is used in something called thermogenesis. It is in the creation of heat. It's called non-shivering thermogenesis, which means it's not our muscles moving. It's purely from the burning of this adipose tissue that our bodies are able to produce heat and energy. What we're used to more so is the white adipose tissue, the unwelcoming little friend around our belly that tends to stick around a little bit longer than we want them to. This is mainly energy stored in the form of triglycerides, which isn't as accessible to our bodies as an energy source. However, it seems that through intermittent cold exposure, BAT, which has something called uncoupling protein 1, has the capacity to be able to activate under those cold conditions and produce a lot more heat. And that is how we can increase our energy output through intermittent cold exposure.
So like Hunter said in the introduction, this is why we decided to read this research paper about this intermittent cold exposure and to see if it really can be a viable source to help people lose that fat on their body that everybody wants to get rid of. So in this research study, they designed it by kind of formatting three different experimental groups. So I named them intermittent cold exposure group number one, or ICE one, two, and three. And so these were different experiments with just slightly differing variables. So in our ICE one, we had three different groups of mice who all had the same mean body mass and fat and had the same characteristics. And we had three groups in ICE one. The first group was going to be our control group, where they weren't put in any type of cold exposure. We had our second group that was exposed to 4 degrees Celsius, so taken from their environment, they were placed in and put into a room of 4 degrees Celsius for 1 hour, 3 times a week, Monday, Wednesday, Friday. And in the third group, they were put into cold exposure for 4 hours a week, or 4 hours, 3 times a week, Monday, Wednesday, Friday. So in ICE 2, similar to ICE 1, except those periods of that intermittent cold exposure time was prolongated to where we have, again, our control group, but then our experimental groups, they were placed into 4 degrees Celsius for 4 hours, 3 times a week, and 8 hours, 3 times a week. And so, in these environments that these mice were kept in, they were given an unlimited amount of food. So, as their bodies were burning more calories so that they could maintain homeostasis and keep that body temperature at its desired level, they were burning more calories than they needed to eat more food. And so, in ICE number three, they introduced something called AM251 to be able to isolate and see if just cold exposure would be enough to really shave off the body fat in these mice. And so to explain what AM251 is a little bit, the AM251 is a synthetic compound that acts as a selective antagonist of the cannabinoid receptor type 1, or CB1 receptor. It was developed as a research tool to study the physiological and behavioral effects of the endocannabinoid and the cannabinoid system in animals and humans. CB1 receptors are mainly found in the brain, where they play a key role in the modulation of various physiological processes such as appetite. But in simpler terms, for this experiment, the AM251 acts as a CB1 antagonist that is going to both reduce food intake and increase metabolic rate. So this is going to decrease the appetite of these mice, so decrease the amount of food they're intaking, while also increasing their metabolic rate. So, so for these four groups that we have in ICE 3, We had the vehicle, which was just used. The vehicle is just a substance that was used to dissolve or suspend the AM-251 into the mice. And so to decrease the amount of variables that are playing in this experiment, they administered the vehicle to all 4 of these groups. And so we have our 2 control groups that were not put into intermittent cold exposure, but one of the control groups was administered just the vehicle, and the other one was administered the AM-251. Then we have our 2 intermittent cold exposure groups, where one was administered just the vehicle, and they were placed into cold for 4 degrees Celsius, 4 hours, 3 times a week, Monday, Wednesday, Friday. And our other intermittent cold exposure ice group, they were administered the AM-251, and they were placed into cold 4 degrees Celsius for 4 hours, Monday, Wednesday, Friday. And so this was going to be able to show us exactly the benefits or the effects that intermittent cold exposure could potentially have, while coupled with an ability to reduce the amount of food that one is intaking. And so for this experiment, they were pretty simple the variables that we were measuring. And so what we were looking at is just the body weight, and the amount of food intake was also measured, and they were recording the fat mass and fat-free mass of this mice every 2 weeks. And so in both groups, they were going to look at the effects that intermittent cold exposure has on the fat mass and the fat-free mass in all of these mice.
Great. So for our results, we have our first figure, and our first figure looks at food intake versus body weight. On our left, we have the food take over the period of time which the experiment was taken, which is 10 weeks. And then on our right, sorry, we have our body weight over a measure of days. So on top, the graphs represent ice 1, and on bottom, the graphs represent ice 2. On graph A and the graphs in column A, we see that they recorded the average food intake, calories per week. And so for week 1, we can look at specifically how the mice that were exposed the longest increased their food intake the most. And that goes the same for ice 1, ice 2, and all across every week, they increase the amount of food they intake. And the graphs in column B show that their body weight increased slightly, as we can see that they were increasing the amount they were eating, so naturally they would increase their body weight. Because they weren't limited on how much food they can take, we could see that they were fully compensating how much energy they were losing during this cold exposure. So to conclude from this graph, we see that the cold exposure had very little effect on body weight and body size, because the mice were compensating for how much energy they were losing. On our next figure, we look at energy expenditure versus time. And so for this one, the scientists used a beta-3 agonist receptor, has some long name called CL and a bunch of numbers. Basically, what it does, it allows us to track and estimate how much energy these mice are capable of burning. So we can see on our y-axis is kilocalories per hour, and on our x-axis is time. So at minute 0, they were injected with this beta-3 agonist, and we can see huge spike in energy expenditure. They were then exposed to the cold for their allotted times, 1 hour, 4 hours, or 8 hours. And we can see that the mice that were exposed the longest burned more energy throughout the study. Our next figure is blood glucose versus time. So they used a glucose tolerance test to see if the cold exposure was actually increasing the metabolic rate for these mice. So in ice 1, we have on our y-axis the blood glucose milligrams per, I want to say deciliter, over a 2-hour time period, or 120 minutes. And so after a full day of fasting, they were administered their glucose test. And we can see from ICE-1 that the group exposed for 4 hours had an increased metabolic rate because their slope was under the control, and the control represents a somewhat normal, or what the rate should look like. And so the fact that it burned through that glucose faster shows that there was an increase in metabolic rate. For ICE-2, the mice were administered this test 2 days after their cold exposure, which is important because we see on their graph that their numbers were somewhat consistently the same with each other. This pretty much tells us that intermittent cold exposure has a temporary effect on our metabolic rate, and it slightly increases it temporarily, which is what we expected and what we were looking for. Now, for our fourth and final figure, we wanted to look at the effect AM251 had on the mice as they're exposed to cold. And so on graph A, we have the same experiment for body weight, or data recorded for body weight. And we can see that the mice that had the AM251 had a huge decrease or difference in body weight, as well as food take, that we can see in graph B. And if we look at graph D, we see that the AM251 also greatly increased the metabolic rate. These are all the things we were looking for. The problem that we came across is that with graph C, energy expenditure, we're hoping that the addition of AM251 and cold exposure would give us that synergistic remedy, that perfect way to lose that body weight. But the AM251 decreased the amount of energy the mice were capable of burning, or the calories that they were capable of burning, showing that they don't work together. They kind of clash, where the decreased body weight and increased metabolic rate is an independent side effect of AM251, and that it wasn't working together to burn maximum calories, increase metabolic rate, max it out. It was more just they were two independent side effects of two different methods of losing weight.
So with that, we can come to a conclusion that there is some very real data that suggests that this may be a potential way to assist in weight loss. Of course, as we saw in the mice, they had a higher caloric intake to account for their higher expenditure, so there was no change in body fat percentage there. But as humans, we have a little bit more control over that. So it does increase thermogenesis, it does cause a higher energy expenditure, and it does increase the activation of beige adipose tissue. And it could potentially even go as far as to promote resistance to obesity. And that is our presentation.
Thank you.
Thank you.
Thank you.